Good morning, everyone. So today we are going to see another compound of boron, and that is Borazine. Okay, so Borazine, or they are also called as Borazole. Okay, so that is what we are going to study. So initially, we will go with the preparation of Borazine. So the first preparation of Borazine was the one that I discussed when I talked about the reactions of diborane. So when you treat diborane with ammonia in 1:2 ratio, it forms Borazine, which has a general formula of B3N3H6. So this is the general formula for Borazine molecule. So this was the first, or we might say the primitive synthesis of Borazine, and this was given by the scientist Alfred Stock. He was the pioneer, as I told you before. He was the pioneer who developed the borane chemistry. So he first gave the preparation of Borazine. Now, structurally, the Borazine looked like the alternating network of boron and nitrogen arranged in a hexagonal manner. At each end, you have your hydrogen attached. Okay, so this is the general structure of the Borazine molecule. So this is the first preparation. The more better synthesis is where we can treat ammonium chloride with the boron trichloride. We generate this particular Borazine species, which can be converted to pure Borazine by reduction with the sodium borohydride. So initially, when you treat the ammonium chloride with BCl3, it forms a trichloro substituted Borazine, trichloro substituted Borazine. So here, what do you see? These hydrogens that is attached to boron is having chlorine there. So if you want to convert this into a pure Borazine, what you have to do, you have to reduce it. So when you reduce it, you can convert it into pure Borazine molecule. Now, if you can do substitution also. So if you have Cl at these boron end, you can treat it with any organometallic reagent like methyl magnesium bromide. So what happens? The chlorine gets substituted with methyl. So you get methyl substituted Borazine. Okay, so you can make boron substituted Borazine as well as by treatment at this stage with a organometallic reagent. Now you can obtain directly the pure Borazine by treatment of ammonium chloride with the or reduction of ammonium chloride using sodium borohydride. Then you will get pure Borazine. Then we can also make substituted forms of Borazine. So I have told you one way of substituting is at this stage you can treat it with the Grignard reagent and you can substitute chlorine with the other alkyl moieties. Apart from that, if you start with ammonium chloride, which is like one of the hydrogen is substituted with any alkyl or aromatic group, then when you treat it with BCl3, what you're going to get is a Cl with all the hydrogens being which is attached to hydrogen. All these would be replaced with the R group. So here, when you did the initial synthesis, what you got was, I'll do that because I think you will not understand it without showing it. So first, when you did this particular synthesis, what you got a trichloro substituted Borazine. Okay. So I told you when you get this, you can substitute these chlorine with the alkyl group by treatment with the Grignard reagent. Okay. Apart from that, if you take, instead of pure ammonium chloride, a substituted ammonium chloride, okay, what will happen? These nitrogens will now not be attached to hydrogen, but rather they would be attached to the substituent that are present on the substituted ammonium chloride. So this is what is formed here when you use a substituted ammonium chloride and react with BCl3. Okay, so when you reduce it now using NaBH4, what will happen? All the Cl will be replaced by hydrogen, and what you get is this particular compound. However, if you now treat with another different kind of organometallic reagent, what will happen? All this Cl would be substituted with the other kind of Grignard reagents. Okay, so this is about the preparation that is of the Grignard, this Borazine molecule. Let's look into the structure of this Borazine molecule. So if you look at the structure of the Borazine molecule, what you see, this is the one that I drew previously on the previous slide. So here you have the borons attached to the nitrogen atom in an alternating manner to form a hexagon, and it is then having at each of the boron and nitrogen you have the hydrogens attached. So it now if you see here, we have lone pairs present on these nitrogens. So somehow we can have a donation happening in this manner. Okay, so if a donation is happening, you will get a double bond here, and you will have a positive charge generated and a negative charge generated. Similarly, you have this particular structure. Another resonance structure you can draw is here, is that if the donation is happening in this particular direction, the double bonds would be kind of interchanged to a new structure. So let me draw that. So this looks like boron, and you have nitrogen, and you have again a boron atom, and you have a nitrogen, and you have a boron atom. Now at each end you have the hydrogen. So that is that you know. Now if the electron transfer is happening in this direction, double bonds would be formed here, right? So since the charge is coming like this, so it would be positive, positive here, negative here, positive here, negative here. So this is another alternating structure of the Borazine molecule. So these are the various resonance structure of the Borazine molecule. So if you look at this structure, they look similar to your resonance structure or the Kekulé structure that you draw for the benzene molecule. Now you can draw a hybrid structure also as you draw for the for your benzene molecule. You can draw a circle like this, and now here you will have your boron, nitrogen, boron, nitrogen, boron, and nitrogen. Okay, so this can be your hybrid structure that you draw for this particular molecule. So this is your resonance hybrid. This can be drawn as a resonance hybrid, and here you will attach all the on each of the nitrogen and boron, you will attach the hydrogen atom. So looking structurally, the Borazine looks like a benzene molecule. Now, because they are isoelectronic to a benzene system, these Borazines are isoelectronic, and structurally, resonance hybrid wise, they look like they have a lot of similarity to the structure of the benzene, and they show some physical similarity also to the benzene moiety. And that's why since they are made up of inorganic elements, these particular Borazines are also termed as inorganic benzene. They are also termed as inorganic benzene. So this terminology has come purely from its structural and some physical similarity to the benzene system. Okay. Also, they are, as I discussed when I was talking about boron nitride, they are kind of isoelectronic to the carbon compounds as well. Okay. Now, as here written down, that inorganic benzene are kind of a misnomer. So what do you mean by a misnomer? That means it is not exactly a benzene molecule. It is a wrong terminology that is used here. Why I'm saying that it is a misnomer is that though they look similar to the structurally to a benzene moiety, but chemically they are completely different from uh, a benzene molecule. So what all reaction that you see in a benzene molecule won't be the same reaction that you would be finding in the case of Borozine moiety. So that is why it is a misnomer. It's not exactly a inorganic analog of benzene because they have a lot of difference between them. So that is why this particular terminology is a misnomer. It's not a clear-cut correct name that can be given to a Borazine system. So this terminology, since it's structurally similar, so this is being used, but it's a misnomer. It shouldn't tell you that they are completely same as a benzene. No, Borazines are not completely same as a benzene, but they are different in their chemical property. Now, if you look at the electron cloud, okay, so in benzene, what is happening? All the p orbitals which are perpendicular to the plane of the benzene ring, they are kind of overlapping, and you have the electron cloud on the top and the bottom of the plane. They are uniformly distributed all around the carbon atoms. Okay. Now, when you talk about the electron cloud on the Borazine, here there would be a problem. Why? Because the boron and nitrogen, they show an electronegativity difference. So nitrogen is kind of more electronegative than the boron. They are more electronegative than the boron. So as a result, what happens when you look at the molecular or the electron cloud picture of this particular molecule, the way in which benzene is there, the pi clouds is uniformly distributed. But in Borozine, the pi clouds are not uniformly distributed, but rather the cloud is more concentrated on the nitrogen atom. That means the cloud is more richer in the nitrogen atom. And on the boron atom, the electron cloud density would be little bit lesser. Now, why this is happening? Because nitrogen is more electronegative than the boron atom. So that is why the electron density around the nitrogen or the cloud density around the nitrogen would be higher, and the cloud density around the boron would be little bit lesser. So it would be a lumpy kind of situation. So when you go from nitrogen to boron, the electron cloud becomes larger and smaller, larger and smaller. So the electron cloud is not very uniform in the case of Borozine, but rather it is lumpy. Okay, it's large, small, large, small, large, small, like that it happens. So that is why this particular thing, it is written down here that they are lumpy due to the electronegativity difference between the boron and the nitrogen atom. So this non-uniform distribution of the pi cloud over the Borazine planar ring system, these pi bonding is weak in nature. So this is not a very strong pi cloud as you find in the case of a normal benzene molecule, but rather they are weak. Okay. So because of this electron rich center, electron density over the nitrogen, nitrogens are more basic in nature. Because of the less electron density on boron, they are acting as a Lewis acid. So because of the electron density difference between the nitrogen and boron, rather than undergoing the usual substitution reaction that you find in the case of a usual benzene ring, what you will find is that here they will undergo addition reaction. So let me explain that chemical differences using the reaction comparison. So what do you see here? Here, when you react benzene with HCl, nothing will happen. There is no reaction in which benzene will react with HCl. So it would be like remaining benzene itself. However, when you treat Borazine with HCl, what will happen? It will add on the HCl molecule, like when you add HCl onto a double bond. Okay, the H and Cl are going to substitute on across the double bond. So similar way, addition reaction is what is happening when you treat Borazine with HCl. So here itself you can see the difference in reactivity. Benzene are unreactive to HCl, but Borazine show addition reaction. Now this is because of the one of the atom is acting as a basic atom, another atom is acting as an acidic atom. So that's why you have the electronegativity difference is leading to the addition reaction in this case. Another difference, benzene, when you treat with bromine in presence of a Lewis acid, it shows substitution reaction, Friedel-Crafts. So this is a substitution reaction. It's not a Friedel-Crafts reaction, it's just bromination. Okay, so bromination may what you are having is not addition but rather substitution that is taking place here. Now, when you treat under similar condition Borazine, what you will have is the addition reaction. So that means on Borazine you will have the Br atom coming at each of the boron and the nitrogen atom. Okay, so instead of the substitution or no reaction, what we are getting is the addition product in the case of Borazine. So this shows the chemical difference between a benzene and a Borazine system. Now Borazines, when usually hydrolyze in water slowly, and they form boric acid, that is H3BO3, and hydrogen gases evolve. So this is one of the property of the Borazine, that over a period of time they get hydrolyzed in the moisture to form ammonia and boric acid and hydrogen. Another difference that you will find is, you might have, when you have studied some complex compound, you have studied ferrocene compounds. Okay, so likewise this is a complex compound where the metal is kind of coordinated with the pi electron on the benzene system. So this is a benzene system, and they are forming a coordinate compound with the pi electrons of the benzene system. However, when you compare a similar compound of the compound with Borazine, so this is a similar compound, only difference is here instead of the benzene, if you have a Borazine system, you are not having a usual pi electron coordination with the metal atom, but rather it forms bond with the nitrogen and they form a puckered structure. So it is not a it's a kind of coordinate bond formed from the nitrogen to the metal atom rather than the pi electron donation to the metal atom. So here when it was benzene, it was a pi cloud that is coordinating to the metal atom, but in the case of Borazine, it is the nitrogen atom that is coordinating, and they are not now planar, but rather they are puckered, having a kind of chair conformation. So this is what you find the difference in the chemical state or the reactivity state of the Borazine and the benzene. So they are completely different, and that is why we say that the terminology that is inorganic benzene is a kind of a misnomer. So it is not exactly inorganic analog of a benzene. Okay. So here I have written down that structure is intermediate between the true pi complex and the extreme sigma model. So here, after a long study, it was found that we don't have a exclusive pi complex in the case of Borazine, but rather we have an intermediate state where it forms a sigma bond as well, but there are chances of also pi bonding forming, but Since you have sigma bonding also present, it completely different from the usual benzene system that you find here in usual organic organometallic compounds. So about these compounds, probably you will be learning in the coordination chemistry. So at that time, you will know what are these pi complexes. Coming now, finishing with this boron and so if you replace this nitrogen with phosphorus, okay, then what you get, those compounds would be more aromatic. Why? Because the boron and the phosphorus, they have almost similar electronegativity. So that will reduce the lumpiness of the electron cloud, and therefore you are going to get more aromatic property probably. Okay, and the ring is planar and the BP bonds are shorter and equal. So a compound of boron and phosphorus are kind of more aromatic in nature. Now, recently, you have also been reported some compounds in which the boron is replaced with aluminum. So when you replace with aluminum, it's called as alumazine. So a lot of studies are being done to make such inorganic compounds. They have different kind of properties which can be used for advanced use as a inorganic compound for synthesizing various materials. So here as such use is not mentioned anywhere. One of the use of Borozine is said that they are actually used as a precursor for making boron nitride. Okay, the Borozine is one of the precursor that you use for the boron nitride, and here also you can produce to some extent ammonia and boric acid also from borozines. So that's all about Borozine. So in the next class, we will be talking about the final compound, that is boric acid. Thank you very much for your attention.